says it right here. Infinite 1D square well. We're going to solve this problem numerically. We already know the answer, yes, is indeed true, but we want to practice solving this using the finite difference method. And we can check our answer because we know what it should be. And then we can use this for other methods too. And I'm not great at this. I'm probably going to make mistakes, but I'm going to plow through anyway because that's what you do to learn. So we have this infinite square well. So it's a one-dimensional region where the two sides have an infinite potential. So a particle must be in this region of length a, where I'm going to set a equal to 1. And it has to satisfy the Schrödinger equation for the wave function psi, capital Psi, which is right here. Now, I've already done something to show you in a previous video that we can just solve the spatial function and do a time-independent Schrödinger equation, and it looks like this, where we have a lowercase psi that only depends on position. Negative h bar squared over 2m. The second partial with respect to x plus the potential times psi is equal to constant e times psi. And we're going to have to kind of figure out what that e is by maybe guessing, maybe already knowing what it is. But we'll get to that. But inside the well, u is 0, so that makes it a little bit easier. That means that we have this equation. Negative h bar squared over 2m, second partial of psi with respect to x equals e psi. That's the equation that we want to solve with the boundary conditions psi of 0 equals 0, psi of a equals 0. That's what we want to do. Now I've done this analytically, I've done it using the shooting method, and now we're going to do the finite difference method. So let's talk about how we take this derivative, the second derivative of x, if I know the positions, the psi at different positions, finite, a finite array. So imagine that I have some points, and they're not evenly spaced because I'm not very good at this, right there, with different psi values, and they all have x values too, and they're all separated by the same amount delta x. So this would be psi 0, psi 1, psi 2, psi 3, psi 4, psi 5, and those two are set. Now let's say I want to find the slope at psi 2. I want to find the partial of psi 2 with respect to x, which I'll write as psi 2 prime, with the prime being the first derivative. Well, I can do that. It's basically the slope at this point. And I can find the slope at this point by looking at the slope between these 2 points right here. So I want to find the slope between psi 1 and psi 2. And that would be equal to the change in psi 2 minus psi 1 divided by the distance between those, which is 2 delta x. And that's a pretty good way to find the derivative at that point. What if I want to find the second derivative, the second partial of psi 2 with respect to x, which would be psi 2 double prime? Well, that's just the change in the first derivative. What I can do is to kind of get an expression for the first derivative there and the first derivative right there, and then take the difference between them because they're separated by a difference delta x. This is the half intervals. So for that half interval derivative, I can use these 2 points. For that second derivative, I can use those 2 points. So this is going to be, I can write this as phi psi prime 2.5 minus psi prime 1.5 over delta x. And that's what I'm going to do. So psi 2 double prime is going to be equal to psi 2.5 prime is psi 2 minus psi 1 over delta x, right? Because it only has an interval of delta x, minus this slope, which is psi 2 minus psi, I'm sorry, that's a 3. This is psi 3. Where'd I get that? I was just going to town there. I did it right there. Psi 2 minus psi 1 over delta x, and all of that divided by delta x. Well, I can pull those delta x's down there, and I get delta x squared. So psi 2 double prime equals psi 3 minus psi 2, and then I have a negative sign, so I get minus psi 2 plus psi 1 over delta x squared. And here I have 2 of those psi 2's. psi 3 minus 2 psi 2 plus psi 1 over delta x squared. Now I can make this generic for any ith element with this. Psi I double prime is equal to psi I plus 1, right? I'm finding it for 2, and that's 3, so this is plus 1, minus 2 psi I, because 2, and this is 1, this is 1 less than that, plus psi I minus 1, all of that over delta x squared. And that's my second derivative with a finite difference. Now, you'll notice that I could go through and find the second derivative for all of these points except for these two. I could not do it for these two, right? Because if I want to find the derivative at psi 0, if I put in 0 here, I have that one, I have that one, but psi 0 minus 1 would be over here. I don't have a point for that. I don't have this, so I can't do that one. Same thing over here. I have psi 5, I have psi 4, I minus 1, but I don't have psi 6. It doesn't exist. And that's fine, because psi 5 equals 0. Psi 0 equals 0. Those are our boundary conditions. Boundary. I'll put CO conditions. But now that I have a derivative, an expression for the derivative, I can write an expression for the ith element using Schrodinger's equation. So remember that the one-dimensional time-independent Schrodinger equation in this well is negative h bar squared over 2m, second partial of psi with respect to x equals e psi. Well, let's just get an expression and replace this with psi double prime. I'm going to go ahead, I think I'm going to go ahead and multiply both sides by this to get it over there. And I'll write this as psi I double prime equals negative 2me over h bar squared psi I. Now I'm going to use my expression for psi I double prime, which was psi I plus 1 minus 2 psi I plus psi I minus 1 over delta x squared. I have a psi I right there. I have a psi I right there. I want to solve for that psi I. And so let's multiply both sides by delta x squared. Psi I plus 1 minus 2 psi I plus psi I minus 1 equals negative 2me delta x squared over h bar squared psi I. Now I'm going to add this to both sides, this term, psi I plus 1 plus psi I minus 1 equals 2. I'm going to factor out the psi. 2 minus 2me delta x squared over h bar squared psi I. And then divide both sides by this, which is just a constant, so it's no big deal. It does, but that e does change. Psi I, messy alert, psi I plus 1 plus psi I minus 1 over 2 minus 2 me delta x squared over h bar squared. So I can go through, if I know the values of everything, if I know all my values, if there's something, it doesn't really matter what they are, it kind of matters. I can go through and use the existing values of psi 1 and psi 2, 3, 4 to find new values. So it'll get a better solution. And then I can use those new values to find an even better solution. And then I can use those new values to find an even better solution. Now, let's go ahead and do that. If I know the energy, it's going to work. And I just need to pick a guess function to start off with. And I'm going to pick a terrible one. And yeah. So, and then we'll find a way to find the energy that kind of works too. And at least I got it to work before. So we need to put this into Python. So let's start with Python and get this working. Switching to Python now. I've already started here. I put some stuff in there. I hope you don't mind. I put a graph so that I can plot everything. I put my constants M, A, and H bar. I put my initial X, my change in X, and my energy, which is something I just guessed because I already knew the answer. But I'll show a method that should work despite that. So the first thing I need to do is to make a list of all my psi values and my X values. And I'm going to need two lists for psi values, right? Because I'm going to go through and change the values of psi. And I'm going to put that equal to a new list. And then I'll set the old list equal to the new list and do it again. I have to have two values for psi. I have to have two lists. Okay. Is that okay? Let's just do that. So here's my first list. XP is my list of X values. Psi P, and I use P for plot, and I'm not sure if I'm actually plotting, but that's what I'm going to do, is an empty list. And psi P2 is my new list of values. I'm going to put the initial value in all of those. Actually, I could put it right up here. Let's put this as 0, 0. They're all 0. They start at 0. They already have a list in there. Is that okay? Now I need to fill in my X values and my psi values and my psi 2 values. And I'll plot it. That's what I'm going to do. X is 0. While X is less than A, and this isn't the best way to do it, but it works. I'm just going to keep on increasing my value of X until I get to A. And with that, I'm going to add new values to my stuff. So I'm going to first increase my value of X. X equals X plus DX. Now I'm going to start adding things to my list. XP equals XP plus X. I'm adding the value to the X's. I need to add my values to my psi's. Psi P equals psi P plus, I'm going to put a constant in there of 0.2. I'm just picking a value. I'm just going to have a flat function like that. I don't want it to be 0 or I don't think it'll work. And then psi P2 equals psi P2, which I don't actually need this. I'm going to change it. But I want something there. So I'm just going to put the same thing, 0.2. And we can change this initial function. Doesn't really matter. Now I do need to go back and I need to set my final value. I already set my initial value for psi to 0. I need to set my final value to 0 also. Those are my boundary conditions. I need those to be set. So I can set the values there. Psi P -1. That's the last element in your list is equal to 0. Psi P 2 -1 is equal to 0. Now let's just plot this and see what happens. So to plot this, since I'm dealing with more than one list, I will use for I in range length of XP. Let's go through all the values of XP, and I'm just going to plot f1.plot the X value, which would be XPI, and the psi value, psi PI. And this will make sure that it's working right. Let's see if it's doing what we'd expect. Okay, that's what I wanted. So I have 0.2 for every value except for these two endpoints right there. So this one's at 0 and that one's at 0. It's a terrible function to start with, but sometimes you just got to do terrible things. All right, now I want to go through and I'm going to say how many times I want to go through this whole calculation. I'm going to calculate new values of I. I'm not going to go through the whole thing. I'm going to start at I1 to I n minus 1. I'm not going to do the whole thing, right? Because those boundaries I can't calculate. I don't have values to calculate them, and I don't want them to change anyway. So let's just do this 100 times. N equals 100. N equals 0. So that's going to be my counter up to the maximum value of n. And so while n is less than n, do the following. And I'm going to give it a rate statement because I'm actually going to plot this stuff too. And yeah, so rate, let's say 100. That would take 100 loops in 100. Yeah, so it'd be 1 second. And we can change that. I want to make an animated graph. I want to animate my plot. And so to animate the plot, I need to use animated graphs. There will be a function called fdata. I'm going to empty that. It's an empty list, and I can add my data points to that and then plot it. Now I want to go through and calculate all my I values. And I don't want to go from 0 to n. I'm going to go from 1 to n minus 1. I can do that. Why am I scrolling up here? Like this for I in length from 1 to range of xp minus 1. So length of xp is the number of things in there. I'm not going to n minus 1. I said n minus 1. The range of the number in there. And I'm going to start at the value of 1. So I don't have to worry about those endpoints. Now, I just need to calculate my new value of psi. And I'm going to put that in psi p. So psi p of I equals, this is just where I'm going to use that equation right there that we had, that one. See that one? That equation right there. That's what I'm going to use. I'm just typing that in. So I'm looking at it right now. I have psi I plus 1, psi p I plus 1, plus psi p I minus 1. All of that divided by 2 minus 2 times m times e times dx squared. All of that divided by h bar squared. So this, not all of that, just this. And now they're all ones, so it doesn't matter. Divided by h bar squared. Oh, yeah. I think that's it. So I went through and I calculated all of my values. Yeah, that's right. And I put them in my new list. This should be psi p2, right? Because I can't, if I'm changing them while I'm calculating them, it's going to just make a terrible mess. So I'm putting all my new values in a new list. Now I can go through and put my old values into my new values. So I can update the other list. For I in range, length of PSIP. I'll go through the whole thing. The 0 shouldn't change. It's fine to go through those. And I'm just going to say psi p I equals psi 2i. And that will set the new values to the old ones. Now, you have to do that. You think, oh, I could just say psi p equals psi p2, but then it does something that you don't expect. It makes those two things pointing to the same thing in the computer. And so if one changes, the other one changes, it doesn't work. You have to go through each element and set them equal to each other. I know, doesn't make sense to me either. Now I'm going to plot that data. So I need to add a data point to the list. So I will go through the list again and I could combine these, but I'm not going to. In range, length of PSIP. F data equals F data plus my X values, which is going to be XPI, and my Y values is psi PI. Now I can plot that. F1.data equals F data, and I can add 1 to my value of n. N equals n plus 1. Let's see what happens. It may be a disaster, and I didn't even save this. Look at that. New finite diff 1D well. Save. And I will give you the code because you know that's what I do. Run this thing, and let's see what happens. I'm kind of scared. Nothing happened. Because there's an error. Range XP is not a function. Range X, I didn't say times. Range XP. Range XP range length of xp. You're going to make mistakes too. So that's just part of doing it. Okay. Now I stopped because I only ran it 100 times. So let's run it 400 times. And we know what this should look like, right? It should be a sine function. And it stopped. Let's just put this to something higher, like 1,000, and run this faster, like 5. And let's see what happens. Because it looks like it's done, but it may not be done. Okay, it stopped again. And I think we're in this situation where it just keeps growing exponentially because we don't know the exact value of E. And now I'm going to use this trick I learned from my friend online, and that's to find the expectation value of the energy in this data, and the next time use that for my expectation value of the energy. So the expectation value, I guess I should switch over here back to the paper. How do we find this expectation value? So the expectation value of the energy uses the energy operator, which is the Hamiltonian, same thing we've been doing. The expectation of energy is the integral over all space, which is easy to do since we only have things from 0 to a anyway, of psi e psi dx. And the energy operator would just be negative h bar squared over 2m psi, the second derivative of psi with respect to x. And if I put that in over here, I get this. I'm going to go ahead and integrate from 0 to a, because that's all that matters, psi, and then this is, I have a negative, let's put this over here, negative h bar squared over 2m is just a constant, second partial of psi with respect to x dx. Now I can use my expression for the second derivative that I had before. And that will be this e negative h bar squared over 2m psi I, and then the second partial of psi with respect to x is psi I, this is I, plus 1 minus 2 psi I plus psi I minus 1, all of that over delta x squared times, this is sum now, delta x. And this cancels one of those, and there we have it. So I need to take my psi value, multiply by this, divide by delta x, and then add up all those pieces, and then multiply by this. So let's make this as a function. I'm looking at the time. Doing okay with the time. I'm going to come down, let's just put it right here. Make my function def e x, because I have an e. Yeah. And I'm going to give it, I want to give it my value of psi, my psi plot, my psi. And I'm going to use, I guess I should give it psi and x. So t psi is a list, and tx is my x value. So I need my x values and my psi values. Okay, let's do that. I do need dx, and I could use the global one, but I'm going to recalculate that as temporary dx. It's tx1 minus tx0. Right, that would be my delta x. They should all be the same. Now I want to do a sum. So to do a sum, I need to start off with something to add it to. I'll call this ET for total as equal to 0. Now I can just go through my whole list. Now, if I want to go through my whole list, I don't want, let's see. Yeah, I want to go from 0, no, I want to start at 1, right? Because every box of squares, I should have one fewer boxes than I have numbers. And so that's fine. For I in range of length of tx minus 1. So I'll go one fewer. Now I just need to calculate my add to my total energy. ET equals ET plus psi, T psi I, times, I'm just typing my equation right here. I'm typing in that equation. T psi, oh no, wait. I need to go, I can't do the whole thing. I'm going to go from 1 to that because I don't have, I'm going to have that same problem with calculating the second derivative. Now I'm going to be short a number, an interval, but I think it'd be okay. T psi I plus 1 minus 2 times T psi I plus T psi I minus 1. All of that divided by T dx. Oh, and I need this. Negative h bar squared oh, I don't need that. Right here, let's just put this whole thing. Negative h bar squared divided by, oops, this. No, that's fine. Divided by 2 times m times. Okay. And then return ET. So that will tell me my my total energy. Over here, when I redo the list, I'm going to just say, every time I go through, I'm going to say E equals EX of my function, psi p, and my x values, xp. So recalculate the energy and set that equal to the energy. And then when I use that energy over here, it should change. Let's just see what happens. Error. Nice. ET is not a function. ET. Oh, that should be plus. Error again. T psi. T psi. Aha. You got to type it right. Okay, so now it's shrinking. It's getting smaller. And it'll keep on getting smaller. So there's a problem there also. Let's plot. Let's do this. Down at the end, I want to make another graph. I'm going to make a graph of energy as a function of n. G2 equals graph. I'm not going to give it a title. X title equals n. Y title. You know what? Because I'm not normalizing it. That's my problem. I don't think that calculates. Yeah, I'm not calculating the energy correctly, so I need to fix that. Y title equals the expectation value of the energy. Width equals, what did I put this one? 500, 250. 500 height equals 250. I need another graph for that. F2 equals G curve. Color equals color dot red. So once I have calculated ET in my function, I don't want to return that value because I need to normalize it. So let's just integrate over psi star psi and use that for a constant. I'm going to call it I equals 0 for I in range, and I can go over the whole thing here because I'm not doing anything weird. Let's just say length of T psi I equals I plus T psi I squared, so I have two of them, times dx, t dx. Right, so that's the integral for each one. And return et divided by I. Yeah. Let's see if that does it. Oh, now down here, I want to print out the energy at the end. Print E equals EX PSP XP. And remember, I'm starting with like at 4.9, so I think that's okay. Okay. What do you know? I think I got it to work. Okay, now, I think I'm going to declare this a success. How do you find the next energy level? There's a couple ways to do that. And this does look like the function that we expect. So that's kind of cool. How do you find the next energy level? Well, I think what I've done in the past is kind of give it, I know that the next energy level is another sign, and I could kind of like push part of the function down below. I'm not going to do that because I was having problems calculating the energy. But overall, I'm pretty happy with this method because I know there's a lot of errors in here. And it seems to be working, and thank you for all the people that have given help, and you know who you are. But I will just stop there, and we're going to use something like this for another method. I think it's really important to understand this finite difference method so that we can use this same basic idea with the eigenvalue problem to solve this, and it'll be really cool. But like I said, the code will be down below, and I'll put a link to my previous shooting method down below too. But if you have any questions, let me know.